In this video, we will look at some skeletal modeling strategies. Previously, we saw how loose coupling of procedures can lead to some confusing dependencies. We looked at how procedures could be organized in a way that reflects and reveals the actual dependencies. The example model that we showed was already making use of skeletal modeling strategies. Let's take a closer look at skeletal modeling. When working on a script, dependencies can get complicated. Certain decisions may have been fine at a certain point in time. But later, as the script evolves, those decisions may need to be reconsidered. In the example, we imagine a script that started with the lofted panels. A set of beams were generated from these panels. And the centerlines of the beams were then used to generate the diagrid, floor and facades. Such a code script could still work. But it would be difficult to understand and maintain. The skeletal strategy advocates the creation of a highly simplified and minimal dataset. We call this dataset the skeleton. Such a skeleton should aim to capture the minimum information required for generating all the other parts of the model. In the example, the skeleton consists of a set of polylines with attributes. Generally, skeletons can include any types of geometric entities, including points, polylines, and polygons. In this example, the skeleton looks similar in form to the final form. But this is not a requirement. In many cases, the simplification of the skeleton may mean that there is limited resemblance between the skeleton and the final form. For example, for an extruded tower, the skeleton may consist of just the base polygon, with an attribute specifying the number of floors. In such a case, the resemblance between the base polygon and the final tower is limited. The different parts are then all generated from the skeleton polylines. The polylines are all centerlines. The various parts can be generated by offsetting from these centerlines. This approach also means that there will be no direct data dependencies between the parts. So changing one part will not affect any other parts. This will make it much easier to develop and maintain your code. Note that the geometric entities in the skeleton may not exist in the final model. For example, in this case, the final model may not require the beam centerlines. So those polylines can all be deleted before the final model is generated. Next, we will look at how to decide what should be included in the skeleton. When defining the skeleton, you need to start by looking at the inputs required for generating each part. These inputs will include geometric entities, but may also include attribute data. The next step is then to look at the relationships between those inputs. In general, you may often find two relationships. First, one input may be a subset of another input. So on this example, C is a subset of A, and is S subset of B. The second type of relationship may be a simple way of generating one input from another input. In this case, we may say that input B can easily be generated from input A. Lofting A can generate B. Based on the relationships between inputs, you may then be able to identify the skeleton. In this case, you might identify input A as being the skeleton. This would be possible, and may be a reasonable choice. All the different parts can be generated from the arcs. However, it would mean that the loft operation to generate input B would have to be repeated in 3 different procedures. The loft operation is quite a simple operation, so it may be okay. But in some cases, such repetition may not be desirable. A trade-off may need to be considered. The decision on what to include or exclude may not be clear-cut. A simpler skeleton may mean more code repetition. In the end, there are no hard and fast rules. The decision is up to the developer. And the decision will depend on the particular model being generated. In this case, we opted to include the stringer polylines in the skeleton. This means that each downstream procedure can choose to extract the required polylines from the skeleton. In this example, the final model does not need to include the geometric entities defined in the skeleton. This is because the skeleton consists of beam centerlines. And these centerlines are a type of construction geometry. But this is not always the case. In some situations, the geometric entities in the skeleton will become part of the final model.